first few hopefully should be not too bad. We talked about that last one. So the first one here, n is 6, so degrees of freedom is 5. 99% confidence, so which column am I looking at? Yeah, the first one, 1% in 2 tails. I'm going to stop at 5, because you got 4.032. So degrees of freedom is 5, t is 4.032. You guys with me? That's very large, right? Because z-scores normally stay below 3 for these confidence intervals. Why is it so large? Because their sample's so freaking small. We basically don't know shit. So that's got to be pretty big to cover our ass for not knowing anything. Here, degrees of freedom is 100. 90% means I'm going to use this fourth column, 10% 2 tails. If I stop at 100, bam, 1.660. Is everybody cool with using that t-score chart? It's actually kind of quicker than the z-score chart. It's a little more direct. This one we talked about, the degrees of freedom is 92, but we effectively go ahead and make it 90. Just to be more conservative. 98% confidence. I'm going to go to the second column. Stop at 90. Bam. 2.368. Yes?
At like 96, would you still go to 90?
Technically you should, but if you go up, I'm not going to dig you for that. If you go up for this one, then I'm going to take something off. I like it. So, I mean, technology-wise, it would fill in all the missing gaps here. That's great. But I do think that you get something from looking at this. It really hammers home the fact that the t-scores do decrease. You can see them becoming the z-score. This one, we already said last time that this is the only one I can't do. Because it says it's not normal, and does the sample size save it? No. So I can't do it with the processes we know. In a Stats 2 class, you'd learn something you can do. But here, too bad we don't have that yet. Jeff hasn't taken a sabbatical. This one, the sample size is not greater than 30, but why does that not matter? We're shit. Yeah, so any sample I take is coming from a normal population. Good to go. So I know I can do something. What is it that tells me Z or T?
You know sigma.
I know sigma, so I can use Z. And for 90% confidence, what will that z-score be? See, this is where I'd use the t-distribution. 90%, 10% 2 tails, all the way down 1.645. No. What is it I just looked up? That's a z-score. I know it's on the t-score chart, but what do t-scores become when my sample gets large? They become z-scores. Why do I need t-scores in the first place if I have a relatively small sample? I'm not sure about S. So they cover the bigger my sample gets, the less I need the t-score to make it bigger. And I love the fact that the sample size is large, because it really just depends on how precise you need to be. So it's up to you. Whatever it is, 1.645. What about part B? It says it's not normal, but the size saves us. So the distribution of all the sample means will be normal. So I can do something. I know S, so I can use t-score. So my t-scored, 11. So my degrees of freedom is, where do you go? 38? Yes, yeah. So a z-score comes from a standard normal distribution, right? I can't remember. I think this book does show this. I didn't put this up here, but this is important, so I appreciate you asking this question. I always forget. I think they got this. Let's see. Hey, shoot, Jeff. Maybe they don't. They suck. They suck. Oh well. Shit. But maybe you can find it on the computer real quick. You have a standard normal distribution. Oh my God. you have a standard normal distribution, right? Okay, I like it. T-scores are going to be fatter, and that's a little bit of an overstatement. But I'll try to bring it up. It shouldn't look that bad. T-score distribution will look normal effectively, but they're not quite normal. So I'll try to look up on the computer here in a minute so you can see the pictures of what they look like. So Z-score chart references the standard normal curve. T-score chart. The T-scores mean the same exact thing. T-scores and Z-scores measure the exact same thing. It's just that T-scores do it using S instead of sigma. So their distribution looks normal, but it's a little bit fatter and shorter. Does that make sense? So, I mean, T-scores mean the exact same thing as a Z-score. They just use S instead of sigma. Yeah. Oh, where am I at? Oh, so what would the T-score be for this? Degrees of freedom 38, 98% confidence. I'm going to use 2% in two tails, stop at 38, and I get 2.429. Is that cool? All right, we'll pretend like that's a yes. 2.429. This one we know we can't do. This one is double good. All right. Sample size was ready to save the day, but it didn't need to. We only know S, so we use a T-score. Degrees of freedom is 60. 99% confidence means the first column, 1% in two tails. Stop at 60, and I get 2.660. I always like that kind of goes with the 1.660 up here. 2.660. It could be just me. I wonder. All right, and then number 3, I give you a quick little problem, sort of like the big one we just did on the other sheet. When you throw this stuff into one of our stats, what do you get? Did it? Say it one more time. 78.286. I didn't really say how much to round it, so it was sort of up to you. What did you get for standard deviation? Which one did you use? S. You just ignore sigma. You go, all right, calculator. That's great, but that's not, it doesn't work here. It's not a population. What did you guys get for S? 15.723. Okay. All right. I like it. Crowdsourcing work. Kicks ass. So now, for the 98% confidence interval for this, what's in the fact that it's I never said. Oh yeah, thank God. I gotta say that. That's the whole point of this section. I was like, shit. So the sample size isn't big enough, but it comes from a normal distribution, so we're good. So what's the degrees of freedom? 6. I want to be 98% confident. That's going to relate to 2% in two tails. I stop at 6, and I get pi, 3.143. All right, it's close enough. That's all I need. We celebrate March 14th. It's Pi Day, so don't give a shit. It's 31415, so in 2015, oh, we partied. Trust me, that means that there was a lot of alcohol involved and all kinds of high. That's it. So now we just throw everything we know in. We know 78.286, depending on how far you rounded that. Give or take 3.143 of these things divided by the square root of 7. Thank you. For some reason I do every now and then with somebody that doesn't understand why we do this. hoping I made a really big enough. S is standard deviation for individuals. I still have to divide it by square root of n to make it work for groups of size 7 in this case. Yes, no, maybe so. That's why it's kind of nice. It's built into the frickin' formula. So you're like, why do I do it? Yeah, you do it. This is in the formula. Don't do it twice, though. I do every now and again get somebody that divides by square root of n and then puts it in the formula and then divides by square root of n again. And you get these nice little tiny confidence intervals. Don't do that. So let's see. What do you get for the error?
59.607.
Do it again. So
59.607.
59, 5. It looks like it should be like 15.
Oh, wait, no.
The error,
Okay, yeah,
yeah.
no.
I'm sorry.
18.679.
18.679?
Yes.
All right. And now, when you subtract this, you get 59.607. And when you add it, you get, that sounds about right. Now, is that a satisfying interval to get a feel for what the real average grade is? Anywhere from an F to nearly an A+. You're like, wow, really going out on a limb there. You with me? Why is that so unsatisfying? For a couple reasons. Good, I like it. That's one reason is 98% confidence is going to take us out decently far, right? Further than 95 would make us. What's the other reason? Sample's really freaking small. Shit. Right? So those two together made this very unsatisfying thing. What would you say is a good, if I said I could tell you the average to within however much, what would be a decent within? You know, what's the average in the class? Well, I can tell you within something. What would you say within how much? How many points would you want me to? You know what I mean? So like you want within 10 points? So it'd be 10 down and 10 up. So I'd say it's anywhere from 60 to 80. Is that satisfying? That's satisfying? Some of you guys are like, that's all right, it's fine. Maybe within 5. So within like one grade level, right? So I could say something like it's from 71 to 81, right? That's getting closer to something that really means something to us. This is kind of bullshit, right? It's like, oh my God. So what would, of course, be your immediate suggestion to make this better? Yeah, look at more grades. Make your sample size bigger. That would have two effects, wouldn't it? If I make my sample size bigger, obviously n gets bigger, which makes the error smaller. But also, the t-score is going to get smaller. So those together make it better, better, better. And, you know, that verifies the thing we knew on the first day. Take a bigger sample, everything's better. Make it random, it's even better. Or balanced. Yeah, maybe. Let me show you a couple things. Oh, and then I'm going to try to find the pictures of the T thing. Oh, shit. There it is. There was one study, I couldn't find the results, that was talking about the amount of bacteria in men's beards is more than some of them. So, if you have a beard, you might want to take a look. So look at all this craziness. So what this study was doing is it's looking at the amount you sleep versus death rate. Right? Or they looked at various causes of death and so forth. I just looked this up, so I haven't even really looked at it. But I wanted to at least show you. There's a lot. I mean, and again, how did I do this? I typed study into Google, and I made it look over the past week. And I get like immediate studies that have been done and released in the recent time. There's nifty stuff about the twin study. They set one guy up and kept his twin on the Earth, and they could study the physiological differences after the one guy came back. So NASA did a big study about that, but I couldn't find the specifics. So down here, oh, I can do this. Where'd it go? Blah, blah, blah. Here we go, somewhere around here. 95% confidence interval, but they actually have intervals. Where'd they go? Oh, there, down here. Okay. So 95% confidence interval for the hazard ratio, blah, blah, blah. Anyway, so I'm not going to get too deep into the meaning behind the study itself, but I just want you to realize confidence intervals are just an automatic thing you do when you're looking at data, just to give the reader a feel for how sure you are about certain things. Yeah, so looks the hazard ratio sounds like, something that's going to make you die or something. So the smaller that is, it seems like the better it would be. You sleep more than 9 hours, it goes way up, but look at the uncertainty. Do you see what I'm saying?
Of that? Like the uncertainty.
Yeah, if you look at you can't really see that too well, can you? I can't really zoom in either. So right here, you see how it's going down, the more sleep you get, right? That hazard ratio. Do you guys see that? It's 1.61 for less than 5 hours, 1.11 for 6. I guess the 7 was a baseline, 1.08 for 8 hours, and then suddenly it jumps to 1.77 for over 9 hours, right? If you're trying to approximate a koala, I guess. But look at the confidence interval. There's a wide range. It's a much larger standard deviation, more than likely, for that, right? There could be all kinds of reasons why somebody's sleeping that much, and one of them could be they have a lot of shit wrong with them already. I don't know. Okay, here's the other one. This one's a little bit more interesting, at least to me. So this was a study, I've already forgotten what the hell it was. Effect of a workplace wellness program on employee health and economic outcomes. I am not even going to get anywhere into the specifics about the study itself, but I want to point out a couple things. After 18 months, the rates for 2 are required, blah, blah, blah. So in the intervention group and in the control group, for engaging in regular exercise, they make a confidence interval for the difference between the two groups. The fact that this confidence interval does not include 0 is evidence that the difference is real. Because according to our results, there's only a 5% chance that we're wrong about this. So maybe around a 5% chance that there really is no difference. So there's a 95% chance that there is a difference. So this guy is going to rule our life in the next chapter. This p-value is the probability that the difference we see is just because of random differences in our samples. Not really because there's an effect. So there's a 3% chance that the differences they saw were just because they happened to pick people that were different, not because sleep actually, I can't remember, this was a workplace exercise, whatever the shit, had an effect. So I would say that's really strong evidence that there is an effect in that one little area that the workplace exercise program had. Are you guys with me? The smaller the p-value, the stronger the evidence there is for a relationship between what you're looking at. So that p-value is going to become huge for us when we start analyzing claims in this next chapter coming. Okay? Are you still going? Yeah. All right, so I wanted to show you that. Yeah. Okay. All right, so I wanted to step a little bit into that next chapter. I want to warn you ahead of time that the problems we're going to do in this next chapter are all going to involve several steps. One of those steps is going to be writing a conclusion about what you've discovered. Yeah, I know. People are like, you put English in my math class. Shut up. You got to explain what the hell you found in statistics. You just have to. The other part of this is there are 5 steps for these problems. When I took statistics, I was taught 8 steps. I've gotten it down to 5 for you. You're welcome. So just to get a feel, I don't even want to get into too many specifics today. I just want to get a feel for what this next chapter, what this type of thing is called, a hypothesis test. What it's trying to accomplish and why it makes sense.
Can we talk about p-hacking?
Say again?
Can we talk about p-hacking?
P-hat?
P-hacking.
Oh, that might come up. We'll see. Okay, maybe. There's a lot of, in general, well, all right, I'm going to leave it till we get there. I don't want to worry about that yet. It's a little too specific about detail. All right. So here's the thing. How do let's see. So if somebody makes a claim, is there something, I don't want to do that, get someone in trouble. Let's say that somebody thinks that a certain teacher always gives out a lower average than other teachers, right? That the average is lower than something always. Let's say you make a claim that Professor Bob always gives out, his average grade is less than, sleep. That's probably the best thing for you. Okay. I'm sorry. I'm making a claim about his total average. I'm making a claim about a population parameter, right? And then we're going to test that claim taking a statistic. So let's say, yeah, that's right. Let's say we think his average grade that he gives is always less than a 70. So the average for the students in his class, less than a 70, right? My calc students will probably make this claim about me. Data sir. All right. Yeah. So how would you go about showing this? Let's say you know a decent number of people that have taken this professor over the last several semesters, right? Can't you take a sample of them? Don't just take them at their word either. Say, I want to see your transcript or something and show me the grade. You with me?
There's some bias, because there are people you know.
Say again?
There's bias.
Oh, well, good point.
Maybe you hang out with losers or something.
Totally true, and I do. But let's get it better. Let's say that you seek out, you're able to get lists of the students in Professor Bob's class over the last several semesters, and you take a sample of those people, not just the ones you know. Good point. Let's say you take a sample of 38 students. So is that a decent sample size? See, now we know. Is that the greatest sample size? No, bigger is always better, but that's decent because that guarantees that the sample means will be normally distributed. I like it. Okay, maybe. And let's say we find an average grade of 68.2. Why can I not? I cannot just stop right there and say, oh, yes, I have shown it.
Confidence intervals.
Nope, we're not going to do confidence intervals. But why can't I not just stop? Isn't 68.2 less than 70? So why can't I just go there? I'm done. I did it.
Oh, you need to explain?
No. It's not that the problem isn't done because you haven't written a conclusion. It's because this came from a sample. And there's always a chance. I don't care how random you try to guarantee it to be. There's always a chance that the sample you took randomly was just lower or higher or different, right? You guys kind of with me? I mean, am I surprised that the sample is different than the population? Assuming this is true, and here's what we do in these problems. We go, all right, let's say it's 70. It's not less than, let's say it's 70. It's not less than 70. Look what we just did, right? That's basically the heart of these problems. Stay with me. Stay with me. You guys with me on this idea? If I take a sample anything, it's not going to equal the population average. I would put a shitload of money on that. Right? They're not going to equal each other. They should be close. If I took a nice random sample, they should be close most of the time. So that's what's missing so far. We haven't analyzed how close that is. So what other information do I need to be able to analyze how close that is in statistics? What do we use to measure closeness? In statistics, what do we use to measure distance? And they use standard deviation. I like it. Okay, maybe. Stay with me now. So if I take a sample, I already know going in that it's not getting. So if somebody says, "I claim that that I can chop wood at exactly 4 feet without measure," you guys with me? So I'm like, all right, do it. So our claim then would be the mean is not 4. He says I can chop wood so the average length of all the wood I chopped is 4 feet. Right? And our claim would then be that it's not 4 feet. That you're wrong. You can't be that precise. With me? With me? I know that any sample I take will not equal 4. That doesn't mean that he's wrong. We just have to see, is our sample that we took far enough away from that 4? So here, is that far enough away from this? In fact, far enough below this to be evidence that the entire mean is actually less than 70. So let's say that we know, well, let's see, at this point we know t-score. So let's say that we know S. We calculate S from this, and we get, what you get, Jeff? 11.298. I like it. So remember this. I'm glad this came up earlier from, I think it was Zachary. I'm glad you brought this up earlier. Remember this formula here, of course. We use the shit out of this guy. We even have this. All right? But the beautiful thing is the t-score measures the same thing that the z-score does. So the t-score is the same formula. So the problem, let's calculate this. How far apart are these two things then? Well, the major problem here is to make this really, really true. Let me see if I can get you guys with me. If I was going to calculate a t-score here, what's wrong with using this guy? What's wrong with using him?
Isn't that the standard deviation for individuals?
Yes, and I have a group of 38, right? So if I calculate, what's the new standard deviation going to be? It's going to be 11.298 divided by the square root of 38. So what do we get there? Somebody help me out. 1.832?
1.833.
1.833?
Round up.
Yep. Okay. She made a friendly amendment. So the t-score formula is actually the same as the z-score formula because they both measure the same thing. The only reason I call it a t-score from this is I know I'm going to have to compare it to t-scores to figure this out. So what's missing right now, what we're going to do in this chapter, I can now calculate the t-score, but what we normally do before we do that is we set up how far away is far away enough. Okay, So for example, I want to show evidence that the actual mean is less than 70. So how many steps down would be sufficient evidence? It's really up to us. If 70 is the real mean, then some of the samples will show up far away from it, right? So if there's a real average anything, some samples I could take could be very far away. Like those 2 confidence intervals today that were far enough away from the real mean that you didn't even include it in the confidence interval. You guys kind of with me? So I can control the probability that a sample could show up in here if that's the right middle. I can set what I want this to be. So let's say I want to be a 5% chance. Let's make it a 5% chance. Okay. And there's a symbol I don't think I've shown you this yet, but I think it's in the book before now. There's a symbol for the area in the tail of something. And that symbol is alpha. I don't know if you guys have seen that in the book yet. Alpha is the area in the tail or tails. So on that z-score chart,
One tail or 2 tails?
yes. So whatever the number of tails is. So let me ask you this. How many tail tests do you think this is? I've kind of given it away because I already drew it. It's only a 1-tailed test. Why? Because where's the only place a sample could show up to be evidence for this? Down here. Any other sample that shows up over there isn't evidence that this is true. So not only does my sample have to be less than this, since it's only a sample, it's got to be really less than this. You like it? So if I said, the average age of Grossmont is 28, and then we walk along and the next 3 people we see are all 50, is that evidence I'm wrong? Really weak evidence. It's only 3 people, and maybe they all came out of some, certain class that appeals to older people, right? So any sample I take will be different, which means any sample I take, for it to be evidence that something is different, it has to be really different. Okay, I like it. So for this problem, let's see. It's related to the idea of like setting a benchmark for something, and you have to pass that benchmark. So let's see if you guys can help me out. How many tails is this in? 1. Now you really see why that T-score chart is set up the way it is. Because I can have 1-tail tests or 2-tail tests. A 2-tail test would be, I think it isn't 70. Then it could be less or more. 2 tails. This one, less than 70, 1 tail. So I've got 0.05 in 1 tail. Degrees of freedom is 37. Can you guys look up the T-score for this? Be careful. Oh, there. So 0.05, 1 tail. So you got to look at the very top. 0.05 in 1 tail. Stop at 37. What do you guys get?
1.687.
Yeah, 1.687. Is that cool? You guys see that? 1.687. Be careful now. That's not quite right. That isn't right. What should I put here? You can do it. Negative 1.687. We're the humans. The chart don't have negatives, but we're like, that's below the frickin' mean. That's negative. All right. So what that does for me. So this is what's variable in these problems is what's the probability of being wrong that you accept. So we're saying here a 5% chance we're wrong is acceptable. That's what sets up how far away my sample has to be. So if the sample If I do the t-score and it gets here, that's not enough evidence to show that this looks right. That's not enough. It's less than, but not less than enough. It's like within the expected variability for a sample. But if I do my sample and I get a t-score down here, that is evidence that it is less than 7. Never frickin' proof, because that's real life, right? But it is good evidence. So let's see what this t-score is. Let's see, what do I got? So it's going to be my data, 68.2, minus what we're assuming to be true. So this is a huge thing for hypothesis tests. What we do with these is we assume the mean actually is 70, which means there really should only be a 5% chance we get something in here. So if we do get something in here, that's evidence that that's the wrong place. It should actually be lower, because we just did something that's very, very unlikely. So what do we get for this t-score? Our data minus what we're accepting to be the middle, divided by, not that one, Jeff, the 1.833. So it looks like we get about -1 almost. -0.9 something. 0.98. Yeah. So did we make it far enough away to show evidence that it is less than 70? Where did we make it? Did we make it far enough away? Did we make it in here? No, because it had to be less than this to make it in there. We only made it that far. We made it less than a step away. So yeah, the mean was less than 70, but it came from a sample. It's going to be different from 70, shit. So not only does it have to be different from this, it's got to be this much different. It's got to be far enough away to show evidence that the population is actually different. So is the mean 70? I don't know. I just haven't found enough evidence to say it's less than 70. That's all this means. So it is very similar to court cases, right? You assume they're innocent and you need to try to find enough evidence to show that they're guilty. Same kind of idea. You say, okay, let's assume it's 70. Let's assume you're innocent. Let me go try to find enough evidence that it's not 70. It's less than 70. I didn't find enough evidence. Shit. 70's walking around free. Oh, you should be in jail. Take the law in my own hands. Don't try. Oh, man. All right. It's interesting. Every time I do this differently because there's a lot to get into. And I know you guys can feel that. I want to start with the stuff that's familiar to us, this idea of distance away from something. What's new to us is this idea of setting up a benchmark to reach. What's it take for a sample to show evidence that the population really is less than 70? The sample's got to show up in here. And that one just didn't make it. It wasn't small enough. It wasn't less than 70 enough. So could the actual mean be less than 70? Hell yeah. Could some dude be guilty that the court found innocent? Oh yeah, right? We've seen that many times. But that's the standard of proof that we have to live with, right? So if I really think this is true, what am I going to do? I'm going to take more people. I'm going to get another mean. I'm going to redo this. Okay, maybe. Now, if you want to, I think that's enough for today, but if you want to, on the back of that confidence interval sheet we did earlier, maybe it's up to you. You can look at this, obviously, if you want to. Those are the 5 steps. This sheet right here, I try to put in red is the concept behind that step, and in black is more of a practical how to do that step. And what Chapter 9 does, just to give you a little preview, is Chapter 9 kind of breaks the sections up, 9.1, 9.2, 9.3. They kind of break the steps up in those sections. It's a little bit frustrating. Just to let you know ahead of time. So next time we'll get a lot more into this idea of how to test claims. That's enough.
Gonna kill you. Gonna kill you. I hope I didn't kill you. Oh, I turned you on. Says now? Oh. I think I really put this guy. Yeah, I heard it. What's up?
For my quiz 3, after my corrections, I had a different grade.
For which one? Sorry?
Quiz 3.
Oh. Let me see one. That kind of sucks. Hopefully I didn't do that for everybody.
I need all the concepts.
Here we go.